So we will slowly get started. Couple of administrative things. How many of you have installed Lisp in a box? Okay, good. The rest of you are behind. Okay, you want to actually see how it works, etc. And if the question that I have here is, how many of you would like to have a separate Lisp recitation lecture? The TA is willing to do it. Okay, so it would be outside the class. Okay, and I will let the TA know. And he's trying to do it. What he mentioned was that it might actually work out most likely well for you guys if he does it right after the class, on let's say on Thursday. Would that work for? I mean, it turns out that pretty much I realized that other than this specific slot, none of you are available ever again. But all I can do is for how many people would doing the recitation right after Thursday's class work? Okay, so there's a large number of people. So what we are likely to do is he will probably either pick that or some other slot, most likely that, and then we will record that, and then you can watch it. Okay. By the way, there is a Anatomy of Lisp lecture which also sort of gives you an idea of how to use Lisp in a box, but this might probably tell you a little bit more. Okay, but it'll be most useful if you actually spend some time trying to use Lisp in a box. How many? Yes.
Can we use a different one besides Lisp in a box?
You can use any Lisp. It doesn't. You don't need to use Lisp in a box. That's just the easiest one that anybody can do, and it's free. Okay. But if you have other Lisps, that's completely fine. Okay. I mean, if it's as long as it's a common Lisp implementation, the stuff that I gave would work. So that's fine. Any other questions? Yes.
Can we use Racket?
What?
Racket?
Racket? What do you mean?
It's a language.
No, I mean, other than, is that a Lisp dialect?
I think so, yeah.
Okay, I mean, Lisp, common Lisp, the code I gave will work for common Lisp. Anything else, if it doesn't work, you need to make sure that it works. Okay. Other questions? So I will let TA know. We'll push in. We'll get back to you on the time. Most likely it will be Thursday right after the class because we do have existence proof that a bunch of people are available. Most likely also it won't be in this classroom. You have to probably trek up upstairs because I think there's a class after this here. I will check if it's available. If it's available, you can do it here. If not, other class. The other thing is Will is going to send you all a mail about the office hours that he's going to hold. I think it'll be on one of the days that I'm not holding. So since I hold the day of Tuesdays or Thursdays, it's going to be the Monday or Wednesday. Okay, so he'll send you the mail.
What class is this?
471 Intro to AI.
Yep, not my class.
Okay. Then, so the other question is registering for the blog. I have asked you, all of you must have gotten invitations. All these people have already accepted the invitation. These, on the other hand, haven't. That means you should. The reason you should is because right after this class today, there would be a thinking cap set of questions. This is something that I do occasionally, and this would be the first one, where essentially based on the discussion in the class, I will ask some open-ended questions. These are not homework, but these are like discussion questions, okay? And then you all have a chance to kind of discuss, put forth your answers, and the TAs and I would be monitoring it, and if there are, particularly wrong things being said, we will correct it. If not, we'll just be listening to you, okay? So, and to be able to post on the blog, you must be registered, and so that's why I make sure that you register for the blog, okay? Any other questions? These are the things that I needed to say. Okay, so last class we were looking at definitions of AI, and basically looked at 4 definitions, of which 3 we sort of looked at them and sort of considered them to be less than needed as a normal definition for AI. So for example, not every AI system has to act humanly. Not every AI system has to think humanly. Okay. I did mention that understanding how humans think might be useful for certain AI systems, because to the extent they are actually handling humans. Okay, but we want like a general definition that captures everything, and then you can always add additional constraints. Okay, so you don't need to necessarily understand how humans think to be able to write an AI system, any general AI system. And similarly, you don't necessarily have to act human. And then thinking rationally is good, except just thinking is not going to help. You actually have to affect the world. You know, how many of you have seen Awakenings, the movie? Awakenings, the movie. It's a beautiful, beautiful movie. It's essentially, I mean, it's one of the few movies I cried like a baby at the end of the movie. It's the classic example of these are people, Robert De Niro, and a bunch of other. It's based on a true story, of course. That these are people who did not have effectors. They were thinking. They had complete cognitive abilities, but there was no way they could affect the world. So we never would know whether they're thinking or not. Right? So that was the situation. And so thinking rationally is not enough, because essentially you would not be able to change the world. So finally we get to this last one, which is acting rationally. And in some sense, that becomes the default definition of what AI systems are supposed to do. So that's what we're going to look at. Okay. So basically, rational behavior is doing the right thing. Okay, and in fact, we'll talk about this in a minute again, but the right thing is that which is expected to sort of maximize some performance metric. And hopefully the performance metric is set by somebody else other than the agent, because otherwise the agent will say whatever I did is what I'm supposed to do. Okay, so you are essentially trying to maximize, you're trying to do an action that sort of maximizes goal achievement. Now, acting rationally doesn't necessarily involve thinking. We mentioned this. Sometimes it can be reflex actions. There may not be much deliberation going on. Okay? But to the extent acting rationally, in some cases, the optimal action can be done reflexively. In some other cases, you might actually have to reason, think about what's the best action to do. Okay? So the idea is the end is rational action. How you get to it, I don't necessarily put a constraint. So that's the general enough definition. Okay? So and in some sense, the point I want you to understand here is, it's not so much that I hate this, this, and this. It's just that this is a weaker definition in some sense. Okay? For example, you can be acting rationally and also add the ability to understand how humans think. Okay? The ability to act like humans. And that would help you if your system is, that will help your system if it's working in the presence of humans. Okay? So that's basically the definition that we'll just stick to. So what we'll do now is, before we get into specifics of algorithms and so on, we'll try to see what would it involve to generate an agent that acts rationally at sort of a black box level. Okay? And then we'll slowly, by the end of today's class, the aim, maybe hopefully in the middle of today's class, the aim is, remember I showed you an overview of all the topics that I'm going to do in this class, okay? Which didn't make too much sense to you, probably because there were just a bunch of topics. The aim is to see why those topics are connected to how to generate an intelligent agent. Okay, so that's the idea. Okay, so that's my intelligent agent, and a pink robot interacting with the environment, and all it needs to do is what action next. That's it. Okay. So to be able to generate, to be able to make this agent rational, we just need to figure out, write a program for it which allows it to figure out what is its best action to do next. That's it. That's all you always are interested in doing. Okay. So the question, of course, is how do you decide that? Here is a very high-level program. Again, these things are put there to sort of give us an idea of organizing our thoughts for now. Okay. So an agent program essentially is taking percepts from the environment. So it has sensors and it's taking percepts from the environment. Okay, and it's updating its memory, and it's basically these are all programs. Okay, so update memory means it's sort of changing this current state that it is in. Okay, and then this program, this is in some sense what we want to write, is it tries to pick the best action among the repertoire of actions that this agent has. And then it does that action, and it also not only does the action, tells its memory that I just did the action. So you should be aware of what you have done. Okay, that's all, and then basically update this, and then you actually return action means you actually do that action. So at a very high level, this is the simplest that you want to understand about an agent. Okay, so the question then is, so basically the issue is how do you choose the best action, right? I mean, so these are all black box programs, and we need to figure this out, how to write them. Okay, the interesting question, of course, is how to do that, and so there are, any agent at all can be thought at this level. It's a very fairly abstract level. It's not particularly hard to realize that pretty much anything that I am doing right now can be seen as following these 3 steps. I'm looking around, I'm updating the memory based on my percepts as to whether people are sleeping, people are listening to me, etc. And then I'm then deciding what's the best action to do. In this particular case, I'm doing a speech action. Okay? Maybe the best action to do is to continue talking. Maybe the best action to do is to throw a chalk piece at somebody and say, wake up. Okay? And then I have done that action. Now I tell myself that I have done this action, and then basically continue again. Okay, so anybody can be thought, any agent can be at all thought of as doing this. Now, if, for example, I decide that my best action is to start dancing right now, okay, that still is an agent. It's just maybe it's not a rational agent. Okay, so the idea is that every agent can be seen as essentially following this. Some subclass of these agents might be rational. Okay, so the question then is what makes agents rational? Again, as I said, you assume that some goals or some performance metric is provided to this agent upfront as to how it will be judged. Okay, and based on that performance measure, I'm picking the action that is the best action for me to do to improve my performance long term. There's nothing wrong in me dancing. Okay, for me, performance is at the end of the semester, what did you think about this course? To the extent I believe that my doing a good dance right now would help that, that's the rational thing to do. To the extent I believe that going through these slides is the best way to increase my chance that you will enjoy the course by the end, that's what I should be doing. Okay, so I'm figuring out essentially rational action with respect to the performance measure I've been given. I don't get to set my performance metric. If I get to set my performance metric, I say whatever I did is what I wanted to do. Okay. So externally, performance metrics are set externally, and the rational action is the one that aims to maximize the performance. Okay. Now the tricky part, of course, is when I do actions, they don't necessarily. I mean, we'll talk about this in a minute, but you can see that actions don't necessarily have deterministic effects. Just because I said this, I can't assume that all of you understood exactly what I meant you to understand. Okay? There is some loss in communication. There is some loss in when I do an action, there may be uncertain outcomes for these actions. So the question then is a particular action good or bad has to be kind of figured out over a long period of time and over a large number of behaviors. Because optimal action, and a particular class, I may have taught rational agents, and that particular class people hated me. That doesn't necessarily mean that you shouldn't be talking about rational agents in AI class. Okay? If on the other hand, 20 years I've been teaching and I'm doing this lecture every time I teach this course, and every time they hate this lecture, then I should start thinking, what's going on here? Okay? So you are essentially considering the action that in some sense optimizes the performance metric in an expected sense. You know expectations in random variables, right? So an expected sense. Okay, now one useful thing, one useful abstraction to keep in mind, this is actually kind of a detail, it's a useful detail to keep in mind, is how do we actually judge agents? Okay, I said performance metric. Performance metric is with respect to the states of the world that the agent goes through. Okay? And this is the most useful thing to think of. So you can think of a behavior as a sequence of states that the agent went through. And this is a more general idea than reaching a goal. Because if all you care about is the end point, then you take the sequence, only look at what happened at the end. Do you see what I'm saying? So for example, what's a good taxi driver? Eventually you took a cab, you wanted to go from airport to ASU, so there's a behavior, a sequence of states that the cab driver took you to, and he or she ended at Brickyard. So if all you care about is reaching Brickyard, then you have that information. But many of us also care about how many hair-raising accidents, near accidents that this guy got us through with rash driving. Okay, how does that come into picture? Well, look, yes, you did get me to, Brickyard, but, you almost got me into 8 accidents. So no tip for you. Okay, your performance sucks because, yes, you reached the goal, but you went through bad states. Okay, so it's a very useful thing to think of history or a behavior of an agent essentially as the sequence of states it goes through. Okay? And it's a useful thing to think also about performance is a function of the history. A special case is you only care about the last state in the history. But a more general idea is to think of performance as the function of history itself. Okay? And so basically you have performance as a function of history. One obviously special case is only last state matters. This is what we think of as goals normally. Okay? A less special but still special case is the value of history is decomposable. In particular, you can think of the function of S1 to Sn, the value of S1 to Sn is some summation of function of Si. That means each state you go through, you get a little reward. Reward can be positive or negative. And the total score you get is the sum of all these. That's a special case of performance. Okay, so this does sort of capture our taxi agent guy. If whenever he got almost through an accident, he gets a negative reward. Finally, for reaching the Brickyard, he or she gets a positive reward. And so you can then decide what is the total value of the sequence that you just exhibited. Okay? And then over a period of time, there are multiple different taxi trips, and for each of them, you compute the value, and you take the average value of the sequence. And that would sort of give you the performance of that agent in expectation. Okay? So on one hand, this, at this level, it looked as if I was talking pretty abstractly, do the right thing. But then this is actually a pretty specific thing. You want to think of performances of agents in terms of the states, the sequence of states that they go through. But that actually begs the question, how do states get defined? What are states? I'm sort of currently, sort of appealing to your intuition. Think of states, the normal states. Okay, but I didn't define them. We will get to that. In fact, one big issue is, you'll see in a minute, one big issue is states can be thought of as black boxes or can be thought of as having structure. I mean, state itself has information. Okay, so a state is black box means this state 75, this other state 99. Okay, state having information basically could be that the state itself is split into a bunch of state variables, for example, which have values. Okay, and the different valuations will lead you to different states. Okay, this is basically, we talk about, when you start talking about this, you need representations for states. And this one is what we will use in the beginning. This is problem solving agents. We'll come back to this. So if you think of states as black boxes, you can still do rational agency, but that would just be problem solving agents. And if you start thinking about the structure of the states, then you need to talk about representations. The logical representations or probabilistic representations. Okay. Okay, so that's basically for how we go about. We wanted to design this, which involves figuring out what action to do next. And any agent at all can be seen as doing this cycle, sense, update state, do an action, pick the best action, and continue. Okay. And then a subclass of them are rational agents, and they can be thought of, essentially rationality here can be thought of as maximizing the expected performance. And then the problem of designing a rational agent essentially is writing this program in a concise way. Okay, that's what we're trying to do. Okay. Okay. Now, if you are talking about agents, one thing we want to talk about is, as I said, you need to talk about percepts. What are the sensing modalities that this agent has? What actions can it do? What are its goals, or what are its basically performance metric? And then what is the environment in which it's acting? Okay. Of these, for example, if you consider, let's say, a cab driver agent, a robotic cab driver, what would be the percepts? What kinds of percepts do they have? Visual perception, auditory perception, maybe GPS perception, okay, those kinds of things. What are the actions? Steering wheel, brake, yell, show finger signs, right? These are all actions, right? So those are all the actions. In fact, sometimes not having a good finger can be a big problem. Right? I mean, you may not be able to show the action that you want to show. Then the goals. Like I said, for cab agents, if you want to think of simpler goals, that's basically just goal of being at a place. You take the passenger and then drop them off in the place where they want to go to. But really, goals can also be thought of more generally as performance metrics over sequences of states. So, get me to where I want to get to without getting me into hair-raising accident. Almost accidents. Okay, so those are the goals. Yes?
The goals will be a singleton set always?
What?
Will it be a singleton set always? Will it be only
No, I'm just saying what sorts of goals a taxi agent might have. I'm not yet giving a specific problem. Okay, some taxi agents, some cab agents probably have slightly bad eyesight. They might have slight, hearing issues. Okay, but the kinds of percepts that we expect, the kinds of actions we expect, the kinds of goals that you expect cab agents to have. Okay, so those are the examples. Now, as far as the environment in this particular case, would be obviously the streets. Okay, what kinds of streets? It could be deserted streets. It could be urban streets. Okay, so. Urban streets, freeways, traffic, pedestrians, weather, customers, all this stuff. This is all part of the environment for the cab agent, cab driver agent. Okay. Just to put this in a different level, how about internet shopping agent? Somebody, a program which does buying and selling on your behalf. So it's an agent. It's actually doing actions. Okay? So if you can still think of them in terms of percepts, actions, goals, and environment. Percepts would be things like get information on the internet. Okay? Actions would be post information, send credit card information, etc. Okay? Goals would be presumably, you probably deputed this agent to get you the cheapest hotel accommodations with the highest TripAdvisor ratings. So that's what it's trying to do. So those could be goals. Okay. Environment is internet, the traffic on the internet, the fact that sometimes internet is flaky. After you click, you don't know whether or not your credit card information went. So you click 3-4 times, and then next month you get 4 different transactions for this ticket, one ticket you bought. Okay. Those are all the usual things for the internet shopping for the environment. Now, the thing that I want you to think about is, what if you don't have any percepts? If you have an intelligent agent and you don't have any percepts, does problem solving become easier or harder? And does intelligent agency become easier or harder?
Harder.
Okay. Think again. There are 2 different notions of hardness. One is hardness for you, the programmer, to write the intelligent agent program. The other is for the agent to reach a certain level of performance. When you say harder, which one did you mean?
So programming will be easy.
Programming will be easier. That's an interesting thing I want you to understand. So if you don't have good percepts or good effectors, you're not expected to reach a certain level of performance. So reaching a performance of a certain threshold would be hard. Okay, but writing a program is easier because you don't have any percepts. So how much thinking are you going to do? You see what I'm saying? Okay, so one of the interesting questions is, should you have more sensors or not? Sometimes I don't want to know. Because if I don't know, then you can't complain that somehow I didn't use the information. Do you see what I'm saying? Humans do this sometimes. So percepts actually, in general, lack of percepts makes reaching a performance, certain level of performance, harder. Although it might make the program itself easier to write. Those are completely different issues. Lack of actions also makes performance harder. Right? I mean, if you don't have very good knives, right, and you only have a couple of big knives, then surgery would be somewhat hard. You can still cut big chunks off of people, but that may not be considered JAMA level performance. Right? Okay? So lack of actions makes performance harder. Goals. Complex goals can make performance harder. Get me to home is easier than get me to home while making sure that you don't get me into any hair-raising accidents and while giving me beautiful scenery on the way. That's a harder goal. You see what I'm saying? Even for a cab driver, get me to home one path. Okay? Get me to home with all these additional constraints. There are only some paths that actually satisfy those constraints. Okay?
Excuse me.
Yes.
So you said when there is no perceptions, it's become easier to program but tougher for the agent. But somehow I feel that when there's no perception, it's easy for the agent to act because it doesn't receive any external stimuli. So it's
No, but what I'm saying is without perception. Notice that in this world that you and I inhabit, right? We don't all have equal levels of perception. For example, you have glasses. My glasses are up there. Right now I can't see what you're saying, who is talking right now, let's say. Okay? So the point is that when I don't have my percepts coming to me, and you have better percepts from the same environment, you get to do more, higher performance. You can reach a higher level of performance than I can. That's basically what I mean. Yes?
But doesn't the performance metrics change according to, if you don't have percept, then you will set the performance metric according to
That's a very interesting question, and that's a politically fraught question. If you have understood what I mean, that's the whole point of affirmative action. Okay, so the issue is, should or should not the performance metrics be changed based on the availability of sensing abilities and effector abilities? We do. I mean, being a civil society, if the fact that this little kid doesn't have proper effectors, and our proper sensors is not her mistake, so a civil society tries to change the performance metric for them. But yet, there are certain levels of certain performances that you can't change. For example, you can't let them drive. Many old people would love to drive. In fact, in Western societies, where especially US, where everything depends on driving from place to place, the day when they take away your driver's license is when you pretty much say, might as well die. And I'm not saying you should, but people actually get really depressed on the, okay? But can we say people who are actually old and so they can't hear, they can't see, they should be allowed to once in a while mow down a bunch of people? This happened. I'm not making this up, right? I mean, like less than 2-3 years back, this old man in San Diego, there was a market where he was essentially driving 95 or something, and he essentially just panicked, did the wrong thing, and mowed down a whole bunch of people. Okay? So unfortunately, there is certain levels of performance that we can't change. Okay? But it is true that your expectations will be reduced. If I already know, I mean, if you started asking me as I started this class, if you guys started asking me, tell me again what is 1 + 1, then I change my expectations as to how this class is going to go. There's no point in asking really tough exams, unless I just want to make my life simple by giving zeros on all exams. Okay, but that's again, that actually is a very politically fraught issue, as I said. I mean, in fact, in the case of little kids who actually have physical disabilities, I personally completely understand changing the performance metric for that. Okay, in the case of big kids like you who pretty much have all the possible effectors and sensors, maybe a bit of hardware in the cyberspace is missing, I shouldn't be changing the exams just because you are sort of cyberly challenged, right? So I try not to, and if you do that, then you're diluting the standards. So this is a big political issue. We won't talk too much more about it. Okay. So this we looked at. Now the question, of course, is underlying all this is we talked about percepts, actions, goals, environment. How does environment change the difficulty of writing the intelligent agent program? And how does environment change the difficulty of decision making that an intelligent agent has to go through? That's what we're going to spend some time right now talking about. Okay, because that actually winds up being much more interesting. It sort of subsumes some of this. In particular, percepts and actions get subsumed in environment. Keep that in mind. Okay, so here is my pink robot, but now with a whole bunch of things written on top. Okay, so this pink robot is getting percepts from the environment, and it is affecting the environment. And there's a bunch of things I wrote here. Okay, the first question I have is the environment? So is the sensing, is the environment observable, or partially observable, or not observable? That's one issue. These are the properties of an environment. Okay, one property of an environment is observability. Can you observe the complete state of the environment? If you can, that's fully observable case. Okay, can you observe? And if you only can get partial observability, that's partial observable case. That means some parts of the state of the environment you can see, some you can't. And when I say see, I mean just sense. Okay, and then if you can't observe anything of the environment, then that's inaccessible, completely unobservable or inaccessible environment. Left to yourself, and I get to say, here is an environment. You get to design an intelligent agent. You can pick this environment which is fully observable, this that's partially observable, this that's completely inaccessible or unobservable. And you're a rational agent. You want to make your life easy. because all that matters is you write this program and then you leave. Okay, which one would you pick? What? Fully observable. So you want to pick fully observable. That's kind of nice. What about any other options? Does anybody think that they want to pick something else other than fully observable? Just remember that it's not performance necessarily. It's just getting done with the best program. So, yeah. Inaccessible. So in some sense, picking the inaccessible environment might be easier sometimes because there's no expectation. Nobody else can do better than you. So, and all of you can write, pretty crummy program and be done with it. Okay? Fully observable at least is next best. In some sense, the advantage of fully observable is you can reach the maximum performance, and probably it's not that hard to write the program to decide what, because you know the state of the environment, you can use that to decide what is the best action to do. Okay, now the middle is partially observable. That's hard. Because sometimes the tricky part about partial observability is right now you don't necessarily know, just from the current instantaneous sensing that you got of the environment, you may not know its full state. But there may be a way of reconstructing the full state if you remembered what happened to the environment through your faulty sensors up until this point. Can anybody give me an example of that? So you're talking about, here is an environment that's partially observable, but then sometimes you can reconstruct more than you can see right away. Yes, sir?
How when you're driving, you
Exactly.
You can't be looking everywhere, but you know there's cars to your side and you're looking forward. You still know there's cars there, so you can't change lanes.
Blind spot. Blind spot is a classic example, right? None of us can see a particular part of the passenger side, middle to back of the car. You don't know where they are unless you change, unless you look this way. And if you're all the time looking like this and driving, then your performance is sort of compromised. Okay, right? So the question then is, how do you figure out? There is somebody possibly in the blind spot. How do you still figure out? So one of the things we do now is we look in the rearview mirror at some point of time. Now we look, okay? And then after that, even if you didn't look, if you haven't passed a bunch of exits, to the extent, cars just don't fall from the heavens into the lanes, there probably are no cars. If it was clear before, it's still clear. You see what I'm saying? That's a classic example of using partial sensing to compute the full picture of the environment. Okay? So obviously partially observable is the more, now the world as a whole, is it fully inaccessible, fully observable, or more like partially observable in most cases? Mostly partially observable, right? Not surprising. So in fact, in all these cases, the middle is where the world will be most of the time. Now the other thing about the environment is static versus dynamic. Static essentially means the environment doesn't change unless you change it. Now I close my eyes and I'm assuming nothing is happening right now. That's what a static world is. Now normally, if in fact teacher closes the eyes, students start dancing, throwing stones and all that stuff. That's why classrooms are dynamic. Okay? So dynamic essentially means the environment changes state even when the agent isn't doing anything. Static means unless the agent does something, the environment doesn't change state. Which is easier to deal with? Clearly static. Which is hard to deal with? Dynamic. Which is harder to deal with? When you talk about dynamic, there are two notions of dynamic. One is, the world is changing. I really have no idea. Things happen. What's the best I do? Just avoid getting run over by the car. Okay. Now, if I'm playing chess, is chess static or dynamic?
Dynamic.
When it's your turn, it's static.
No, I mean the overall chess game. Is it static or dynamic?
Dynamic.
Dynamic, because the other agent has an effect on the board. Now, should I just assume that chess is dynamic in the same sense as Milliview traffic is? No, I should model the opponent. Okay, I only have one opponent, and I can actually learn about how those opponents work, and then use that information to my advantage. So in between static and dynamic, where there are faceless agents trying to get you, are agents with faces who are trying to get you. And there is a theory in genetics that the reason we needed the brains we have is not because we needed this big a brain to run away from the tigers. You don't need this big a brain to run away from the tigers. We needed these brains to deal with each other. We had to reason about other people's intentions and reason about whether or not they can do harm to us and strategize, counter-strategize. It's a dynamic world where I am reasoning about the intentions of the other agents. I'm modeling the other agents. That's sort of the middle. And those who model the agents well have higher level of performance than those who think, who knows, things happen, so I just do my best. So they too will reach a performance, but that won't be as high as those who would model their agents, model their opponents. Okay? And so just like partial observability in the middle, which is harder, modeling the agents, dynamism where you have limited number of agents, or multi-agent scenarios, where you understand the intentions of the agents, that helps a lot. Okay? But that's harder, more work. Okay. That's static dynamic, that's observable, non-observable. And then actions. In the case of actions, the minimum thing we want to talk about is deterministic versus non-deterministic versus stochastic. What's deterministic? I'm lifting this. Okay? If I actually can, think in my head that when I decide to lift it, this would be airborne. That's deterministic action. So I know exactly what the effect is going to be of my action. Okay? Non-deterministic, if I have a coin, I'll toss it. I do not know what the outcome is going to be. It's going to be either heads or tails. I don't know. I don't even know, typically, unless I know something about the coin and how fair it is, I don't even necessarily know what's the probability of heads versus probability of tails. If it's a fair coin, it's 0.5, 0.5. In between is stochastic, where I have at least some probabilistic information about what outcomes are more likely to come and what outcomes are less likely to come. Okay? So again, deterministic, stochastic, non-deterministic, which is the easier case for writing intelligent agents? Deterministic, which is at least next easy case. Non-deterministic, because it becomes hard to give guaranteed plans, guaranteed sequences of actions that will ever reach anything. Okay? Can you give me a guaranteed plan that will get me heads when I toss a coin? No. Can you give me a guaranteed plan that, as you keep doing it, you'll at least get one head? I only get to do a finite number of tosses, and by the end, I must have gotten at least one head. A guaranteed plan. Can you give it to me? No. But do we give up? No. We just say, if you toss like 10 times, there's a pretty high chance that at least one head will come. The high chance is the probability. Okay? So the non-deterministic guys won't even be able to handle a class of problems where you're asking for probabilistic guarantees. Whereas the probabilistic action representations, if you have those, you can handle more problems. More problems, just because you're able to handle, that means more work for you. Okay? So that's regarding the actions. Any questions? Okay, by the way, the normal thing, this is the second class, so I'm kind of somewhat nicer. But unless you are unable to see these slides, you are not going to be allowed to use your laptops to do anything else. The only thing that you can use laptops for in my class is, because of your visual acuity problems, you can't see this far, so you're putting this slide there. Okay? Please follow that. Yes, there was a question.
You go over instantaneous.
Yes, okay. Actually, that's sort of a secondary issue. In terms of, I mean, this is a bigger issue, but the secondary issue is an instantaneous action is as the action takes instantaneous time. So you are in a state, you do an action, instantaneously you're in the next state. A durative action takes time. As you're doing the action, time progresses. Normal actions are actually durative, but it's easier to handle instantaneous actions, or at least act as if the actions are instantaneous. This is a second order issue. For this, you need to do temporal reasoning. You need to actually reason about time, and as I am doing my action, people can stop my action from succeeding. So for example, right, I have decided to go to Los Angeles, but it takes time. So if you want to, if I already left my home and I'm on my way to Los Angeles, you can still stop me because it's not an instantaneous action. Do you see what I'm saying? You can, stop the agent from succeeding. If the other agent is an opponent, then you can stop them from succeeding because their actions take time. Okay, all sorts of things can be happening while the action is happening. Okay, now, so I would still think this is a second order issue. These are the three primary issues, and a fourth primary issue is, actually no, I think we already talked about, static versus dynamic, observable, partial observable. Now, partial observability and observability is in some sense connected to sensing. Perfect versus imperfect sensing, okay? So the interesting issue is that an environment might be inaccessible for everybody versus it's actually accessible if only you have the right sensors. Okay, and in that case, essentially you're thinking in terms of sensing. So, but this is connected to, so the point to understand here is for two different agents working in what you and I will call the same environment. For one agent, the environment might be fully observable. For the other agent, it might be partially observable. And for the third agent, it could be inaccessible, depending on the kind of sensors they have. Okay? And once again, of course, you know how the difficulty of the problem changes. Since I talked about this second order issue, I'll also talk about this second order issue, which is if you have goals, you can have full satisfaction. That means I tell you what are your goals, and you must satisfy all of them. If you don't satisfy even one, you fail. If you satisfy all, you succeed. That's one case, where it looks as if I'm being really strict. The other case is here are all the goals. And if you get this goal, you get this much reward. If you get this goal, you get this much reward. If you get part of this goal, you get part of the reward. Okay, which is easier?
Full.
Easier for who? Easier for who? So who thinks that undergraduate life is harder than graduate student life? All undergrads think this. Right, man, I mean, people tell me that this homework is due this day, this exam is due this day, blah, 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 blah. Whereas the PhD students, they get admitted and they're told, you just do PhD whenever you feel like, and you're done. And any specific day you wake up, it looks like, PhD much farther down, today is a good day. Today I don't need to do anything. There's no exam, there's no homework. Why do I need to worry about my dissertation? And how many people actually complete PhD? Not that many. Because essentially what you miss is when I actually structure the course and say, here is the, homework deadline, here is the project deadline, etc. It's not just to make my and teaching assistants' life easy. It's to make your life easier. That's called structuring. I am structuring. Ultimately, really, when you take this course, you're supposed to understand AI. That's all that matters. Okay? In fact, what I really would like to do is towards the end of your life, when you're on your deathbed, I come and check whether or not you understood AI. If you did, you get the grade, otherwise you didn't. Right? But I kind of structure it and say, here are all the various homeworks, and then blah, 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 and then you get a feel, you get a sort of a feel that, how you are progressing towards satisfying your overall. Okay, once again, actually, full satisfaction, while it looks like a reasonably strict requirement, it actually makes your life simple. Okay, high school is way more structured than college. College is way more structured than PhD. PhD, my friends, is way more structured than life. Right? Right? Nobody tells you to do anything. And yet there's a performance metric. Okay? So it looks as if partial satisfaction is a good thing, but it's not necessarily a good thing. In fact, it requires a lot more, you have more flexibility, so you have bigger string to hang yourself with. But the string can also be used to improve your performance. I mean, there is something to be said that when I structure your life, I might be doing disservice to at least some of you. Okay, because maybe left to yourself, you could have done a better job. Maybe you could have just avoided this silly homework for today and instead did some Nobel Prize winning, work today, and then maybe come back to this homework much later. But by structuring it to all the class, I'm sort of structuring it to the median intellect here. Okay, so I might be kind of, robbing you off of your, Nobel Prize. But then, the advantage on the other hand is you essentially can just follow my directions, and then you have a certain, reasonable threshold of getting some performance. Okay, so that's basically all about environment. So environment can be accessible or inaccessible or partially accessible, deterministic or stochastic or non-deterministic, static or dynamic. And then the two other things that are here I didn't put there are, one is episodic. Episodic means you get evaluated over an episode. Okay? And then after this episode is over, then again I'll get to evaluate you separately in this new other episode. So for example, last semester you took this course. You didn't do all that well, but I don't know this. I'm not going to make your grade today be dependent on last semester's grade. You get to sort of, improve, start fresh again every semester. Not completely, because there's this thing called GPA, which is sort of adding up all your performance across the board. But a little more episodic. Your normal life is a little more episodic. The university life is a little more episodic than normal life. Normal life is not at all episodic. Ask the presidential candidates. Whatever they said or did, 15, 20 years back, is still coming to haunt them. Right? It's not like, I did it last semester, man, you should forget about that. I'm now in a completely different, that's not the case. When you go to that level, essentially life is non-episodic. Whereas writing an intelligent agent is easier if you're writing it for an episodic environment. Okay? And the other one is discrete versus continuous. That's sort of, less of a deep idea. It's basically whether the state space is discrete, that means there are a finite number of states, are continuous, that means there are infinite number of states and essentially they're dense. So real valued. So for example, if the state variable is a real number, then if any of the state variables is a real number, then there are continuous states. That also makes life harder, because continuous math is sometimes harder. Actually, not always. Sometimes discrete math is harder than continuous math. Okay. Anyway, so here are some examples. Solitaire. Is it accessible or inaccessible? People who have trouble with solitaire, is it accessible or inaccessible? Is it deterministic or non-deterministic? Is it episodic? Is it static or dynamic? Solitaire, static or dynamic? Dynamic. Static, that's the name of the game. Okay? And discrete, right? Backgammon. Backgammon is a game, right? Basically. So again, it's partially observable. And it is not deterministic because somebody is throwing a dice. Okay? And it is episodic. And is it static? Why is it not static? So what happens if other players play? I don't know actually backgammon. What happens if other players play? Is this a strategy game? Okay, then obviously it matters. Okay. Internet shopping. Obviously not fully accessible, partially accessible. Deterministic to the extent network when you click, submit my payment, and if it's deterministic, that means every time it goes through. If every once in a while the network freezes, that means it's not deterministic, right? And then static versus dynamic, it depends on, there may be other agents who are trying to buy the same thing that you're trying to buy. And so you need to come up with a strategy, bidding strategy. So it's essentially not static, okay? And then taxi world, everything is out. Actually, I just, this is just a summary of what I said in the last several slides. You can read this later, okay? And then that's basically a way of looking at how each of those scenarios are deterministic, are accessible, are episodic, or static, or discrete. Okay, that's about environment types. Now, clearly, as I said, the hard environments are inaccessible or partially accessible, and the hard actions are partially in the non-deterministic or stochastic, and so on and so forth. So if you would like to do the simplest agent first, which is what we'll do in the beginning of the class, we would like to go with accessible, deterministic, episodic, static, discrete agent. And what if most of the world doesn't have that kind of environments? Well, what do? Then there are two possibilities. One is you use wishful thinking. You assume away the complexity of the environment. Act as if the environment is deterministic even though it's not. And if you have good enough sensing, then, so basically I will assume that tossing a coin always gives me heads. And I'll toss it and then look, hey, in this particular case, somebody stopped it from coming heads. So I'll do it again. Okay? So in a sense, if you sense and redo actions, that's one way of handling more complex environments. So you can still be doing your reasoning as if, thinking as if the environment is simple, and do additional replanning, additional redoing of actions based on sensing when things go wrong. Now obviously, if you do this, you are likely to have a lower level of performance than somebody who actually knows that the environment was not deterministic upfront, and they have taken that into account in coming up with their actions. Okay, but this will be a way, a lazy person's way of designing an intelligent agent that will work in a pretty complex environment. And in fact, that sort of brings this issue that just because the environment is complex doesn't mean that the agent has to be complex. Okay, and a very famous example of that is this allegory of Simon's ant. Okay, so Herbert Simon is one of the guys whose mugshots I showed last class to you. Okay, Simon and Newell are one of the two of the 4 people who sort of started the field. And Herbert Simon essentially talked about this point that what might look like highly intelligent and premeditated action could just be an emergent behavior because of a very simple agent acting in a very complex world. And so he's talking about an ant, and he's looking at the ant from like a ceiling, okay, on a beach. And then he sees the ant kind of making what looks like a highly complex maneuvering. Goes to some place, comes back, goes like this, comes back, goes like this, comes back. It looks as if it has figured out B-splines and various other high-flying curves, and it's using those to show its motion. And so it should really have pretty darn big brain. But it's an ant, very small brain. What is it doing? What it's doing essentially is it's saying, keep walking until you hit your head, in which case come back, turn forward. Roomba the robot is current version of Simon's ant. Now, how many of you have, you're grad students, but anybody who actually has money and bought a Roomba for cleaning their environments? I mean, students never do that, but anyway. So Roomba is this little, robotic vacuum cleaner, and clearly it doesn't have a big brain. and it's basically circular, so that when you hit something, you can always turn back and move on. And you can put lots and lots of stuff in Roomba's, path, and it just, as long as it's not like a glass of milk which it will hit and then throw out, little kids are okay mostly. They'll just basically hit the little kid and move on, okay? And it looks as if it's a pretty, smart-looking thing, except essentially it doesn't have any goal-directed behavior. It's just avoiding avoiding obstacles. But thankfully, most of the time, all it is to do is it has a lot of time on its hands, and it just has to keep, randomizing its motion so that there is an expected coverage of the floor area over a period of time. And then, it gets cleaned. Okay, so that's the point. Just because the environment is hard doesn't mean that the agent has to be hard. We can decide to go with a very simplistic agent. In fact, much of AI, one of the things that we talk about in representation issues is despite what we think of our brains are woefully inadequate to deal with the complexity of the world. There's a lot more complexity of the world than we actually can deal with. So what do? We abstract away the complexity. Okay, and so any representation mechanism which will allow you to say, when I do this action, X will happen with this much probability. Y will happen with this much probability. Anything else in the world can happen with the rest of the probability. That anything else is essentially saying infinite number of things can happen with this 0.001 probability. That's a great way of compactly representing what is essentially sort of fractal-like, knowledge that you have, where there are lots and lots of special cases. Special cases have special cases have special cases. If you write all of them down, first of all, your actions will look 8 pages long, and then the agent will just stare at the action and not do anything. Okay? And so you need representation languages which will allow you to model the world with your small brains. And you think you have a bigger brain than Ant, but Ant also has the same issue. Okay? Now the other, of course, is if you don't want, the general idea is either you can go with a simplistic agent, or if your brain is slightly bigger, then you might be able to put an agent program that actually handles some of the complexity of the environment more directly. Okay, in which case your overall performance would be higher. We tend to think that we perform better than ants. Ants may or may not agree, but we tend to think that we have this goal-making ability, and we can reach, it's not just we just keep, hitting walls and moving out of the walls. We actually have goal-directed behavior. And we sort of tend to model each other. We tend to actually look at the world, look at the other agents, and we look at our ability to sense the full state of the world and use that to improve our, the perception of the world over a period of time. Okay, and so that way we get to reach higher performance than the smaller ants, for example. Okay, but given a threshold of performance that you need to reach, as you keep making the environment inaccessible, non-deterministic, non-episodic, and non-static, you increase the complexity of life in your program. Okay. Okay, so last thing that we're going to do today, and we probably have to do a little of this next time too, is essentially we have talked about the fact that you have percepts and actions and goals, and all of these are sort of connected. Some of these are connected to the environment. Goals are the only things that are not connected. Goals are externally imposed, but percepts and actions are connected to the environment, in essence. Okay. Now I want to write agents, and I want to think of what black box pictures can I draw for the agent programs. Okay. And in particular, I'll look at 3 at least, maybe 4, simple reflex agents, which in essence, basically have a set of rules saying if you are in the following state, do this action. If you are in this other state, do this other action. The program is easy to write. Its size could be big. You need a huge big table, okay, which says this state, this action, this state, this action. And the agent looks at the world, gets the state, and does the action. That's the simple reflex agent. So let's start with that, and then we'll talk about why in some sense it's obvious from the discussion we already had here that, if you are taking the current percepts, presumably the simple reflex agents, what they do is this. They have the environment, the sensors will give them the current snapshot of the environment. Okay? Presumably, we'll assume that, environment comes essentially as like, sensing from like the visual sensors, sound sensors, touch sensors and everything. From them, let's assume we converted them into some features, state features. Okay? Then you now know, currently, what you know is based on the sensory information of what the world is like right now. And there's a big table you have. This is the one that you fill when you write the program. Condition action rule, saying, if the world is like this, do this action. If the world is like this, do this action. Okay? And then the agent basically looks into this table and then picks the action that corresponds to what the world is like and does that. This is a reflex agent, essentially, as I said, if you are standing in a busy street and all you're trying to do is duck traffic and survive for extra few seconds more, right? Then reflex agents are pretty good. Okay? If you see a car coming from the right-hand side, move left. If you see a car coming from the left-hand side, move right. If you see a car coming from the front, do something. If you see all 4 cars coming, throw up your hands and start praying or whatever. Okay? So those are your condition action rules. Okay? Now the question then is, can every agent be written this way? Now there are 2 issues. One is, many interesting agents than you may have realized can be written as condition action rules. So one issue would be the size of this table would be really, really big. That's one issue. The second issue that I want to worry about is, and if the table is big and your head is small, you probably can't hold the table. This is an issue. Remember, it's like, so basically, a reflex agent may not be able to handle every level of performance, because to reach a certain level of performance, it might need a lot more rules. And you don't expect it to have them. There's not enough memory to write them all down. Okay? The other issue is, even if you have the memory, can you write everything such that you can reach a certain level of performance? If memory was not an issue. And that comes back to the problem of blind spot. What you're doing is you're deciding based on the current snapshot of the world. In a fully observable world, current snapshot gives you all information you will ever need to know about the world. In a partially observable world, you need to take the current snapshot, combine it with what you have seen over the previous amount of time. Okay? And then figure out really where you are, and then decide what to do. So that's what drivers, driving on interstates do, basically. Right now, the rear view mirror says there's nobody behind me. Does that necessarily mean that there's nobody behind me? For that, I need to take into account, okay, last few seconds back, I did look back, there was nobody. After that, I only keep seeing trees on my side, no exits. And so probably cars aren't falling from the heavens, and so I still am clear. So now I know that actually, it's safe for me to shift into the next lane. So to do this, I reconstruct the state. Okay, just because you have eyes doesn't necessarily mean you know where you are. If all of us have eyes, right? You go to a mall. How many of you have gone to mall? Everybody goes to mall, right? And then they basically have this map and say, here you are. Why do they have to tell us that? Because you don't know where you are with respect to the map. Just because you saw the current store. In fact, typically what you do is, if that map doesn't give you enough information, basically you may be able to reconstruct your position. From, okay, I have seen this Banana Republic here, this gap here, so I must be in this, second quadrant of the overall mall area. And I use that to reconstruct my state. And once I reconstruct the state, then I can use condition action rules. Okay? So the question is, so basically even basic survival needs state information. Not just the current snapshot, but what is the true state of the world. And if it's not a fully observable world, then you need to reconstruct the state. This is called the state estimation problem. And it's a classic problem. Okay, basically you get partial information about the snapshot of the world and you combine them with previous pieces of information plus your background knowledge to figure out. In the case of driving, you use background knowledge, saying cars aren't dropping into the right lane next to you. If you are playing some video game, cars are coming all over the place. They don't necessarily follow this background knowledge. Okay, so use that to figure out what the world is like right now. So now you suddenly have more boxes. So I still get sensory information about what is the current state of the world. Okay, and then that tells me what's the current snapshot. And I have in my memory the current state of the world up until the most recent observation. So that is sort of the combined wisdom I have acquired about the state of the world based on all the observations I have done until then. So the state is sort of a compact representation of what I think the world is really like right now. And then I do an extra observation. Now I basically have to reconstruct what is the true state of the world based on that. Okay? And to be able to do that, I need to have information about these two. How does the world evolve when I'm not looking at it? In the case of traffic, I have knowledge saying cars just don't drop from the air. They have to come through the exits or entries. That's part of the knowledge of the world. I need to know that, otherwise I can't just assume that just because there was no car 3 seconds back, there is no car now. And then, what do my actions do? So for example, I saw a few minutes back and there was no car, and then I took exit onto a different, in the last few minutes, I took an exit onto a different highway. Can I just assume that a few minutes back there was no car before, so now there's still no car? Of course not. I've changed my highway. I'm in a different highway now. Right? I have less knowledge about where I am right now. Okay? So you need to understand what you did and how it affects the current state of the world. You need to combine this and the snapshot that you got and your current estimate of the way the world is to figure out what is the true estimate, what's the best estimate you have of what the world is now. Then you know where you are, and once you know where you are, you can still use condition action rules to figure out what to do. So for example, drivers can say, if you think that there may be somebody in the blind spot, don't change lanes. That's a reasonable rule. You can do that. But to be able to do that, you have to do this much amount of reasoning. And the last thing for today's class is, if you go through all of this, state, how the world evolves, what my actions do. In essence, I have so much knowledge about the world that I can think in my head. If I know what my actions do, and if I know what state I am in, I can simulate in my head, okay, so I'm in this state, and I want to be in this happy place somewhere here, and I can do this action, and I will get these states. This state looks more interesting. Let me go farther on that. Only in thinking, not in actual doing. Okay? And so in my head, I basically search, I reason with respect to the knowledge I have to figure out what is the full path that will take me from where I am to where I want to be. Okay? And then I would just do the first action in that path. That advantage of that is, the disadvantage of this is condition action rules are one size fits all. The agent must essentially compile the goal into the condition. Okay, if the goals change, and if you have not thought about these goals previously, you will not be able to come up with optimal action. Okay? Whereas, since I have all this information, all I am doing now is throwing one extra piece. What will the world be like if I do an action A? notice that I have this, and this from the previous slide. I had all the knowledge that I used just to reconstruct the state before. I'm using the same knowledge to also think, what will the world be if I were to do this action? And from there, I can then, instead of having condition action tables, I can just have top-level goals. And then I can decide what action must I be doing to eventually reach these goals. That's goal-based agent. Okay? So it turns out that this was the course overview we showed here last time. And I'm going to show a picture now. I'll come back to it next class. In essence, the pieces of the course that we do are connected to this picture. Okay? To be able to figure out what action should I do to reach the goal, that's reasoning, search, planning. Those are the things that we do for doing that part. To be able to figure out how to represent the state, how to represent your knowledge about how the world evolves, how to represent your knowledge about what your actions do, you need to think of some representation mechanisms. For that, we will talk about logical representations and probabilistic representations. So this is the representation, this is the reasoning. The only thing that's missing is, if I were to tell you the representation, somebody has to write down this knowledge about how the world evolves into that representation so that the program can use it. For small programs, you, the programmer, will write it. For large programs or programs working in reasonably complex worlds, you may only be able to write an approximate model of the world and expect the agent to figure out more knowledge as it goes along. Okay? So you do have to come into this world with some prior knowledge. In fact, we do come into this world with a humongous amount of prior knowledge. We'll talk about this later some other time. But we come into this world with humongous amounts of information about what are good smells versus bad smells. Even though we have no actual experience about them. And how to swim. At the moment you're born, you do know how to swim. And then 15, 20 minutes later, you'll sink like a stone, and then you take lessons to figure out how to swim again. So we come into this world, and similarly language, we come into this world with a universal grammar, which is sort of good enough to specialize to any language that's being spoken by the bozos around you. Okay? And every human language, you can take a kid who's born in Desert Sam and take them to an African country, and they would speak the local language. No problem. You can take them to a wolf country, they won't speak the local language, to the extent wolves have languages, because the general grammar they have will not be able to capture wolf language, if there is a wolf language. So we do come into the world with a lot of prior knowledge, but we also learn to improve that knowledge. Okay? And so the learning part, when we get to that, it is about how to improve the model. Most of us don't expect to start from scratch with no model at all. We assume that the programmer will write at least an approximate model. In the beginning of the semester, we'll assume they'll write the full model. And then focus mostly on how to write it and how to reason with it. And when we talk about learning, we'll talk about how to improve the model, at least from experience. That's what this course is. Okay? We'll come back and start talking about one of these agents.